today in the lab, I don't know how many of you have finished the arrival time, execution time, and create one cloudlet. Yesterday we showed you. If you did that, today we try to start a very simple, the cloud sync doesn't give you any scheduling. So we need to actually do a simple one and then progress on Monday a stronger one. Okay. Today I'll talk about heuristic resource provisioning. I think everybody does this. So I will, instead of actually enumerating these are the scheduling, I will talk to you about the techniques, the problems, and the issues with heuristic resource provisioning and scheduling. Now, when we talk about resource provisioning, we actually talk about resource management. And within resource management, there are subclasses or sub-components, which includes resource provisioning, resource scheduling, and so forth. So we will talk about overall resource management, but the focus is on resource provisioning and scheduling aspect of it. Now, the reason we talk about resource provisioning is resource allocation is actually a recurring issue. It has been there before us. It will be. So now if you look at why resource allocation and scheduling is very complex in the cloud computing environment, I will see that why is different than the other distributed systems. Now, with the invention of the fog computing, Internet of Things, or different applications that we call killer applications, the whole scope of the scheduling changes. So it is really one of the problems that will never be solved, but there will always be a good solution for it. So, as I said here, it remains a hot topic in many fields, in operational research, in industrial engineering, in computer science, in many fields. You will find scheduling one of the very serious problems that many people are trying to solve. So today we will look at heuristic approaches, and this is again the cloud data center model we will use. Now, this is the same as you can see. Cloud consumers prepare a set of jobs and then send it to be executed here, and then the result is sent back to the cloud consumer. This is a very simple flowchart or diagram that shows how cloud users send information and request and then get back the information. But here is what we concentrate on. These are three different things. Resource provisioning, you see from here to here, I refer to this as resource provisioning. And from here to here, I refer to it as resource allocation. And from here to here, which within physical machines, I call it virtual machine scheduling. So these three are completely different and separate resource management components. So when we actually talk about scheduling, task scheduling, when people talk about task scheduling in cloud computing, sometimes I get confused between these two myself. I don't know which one actually they're specifically talking about. So because tasks are mapped into virtual machines, and virtual machines are allocated to physical machines, and the scheduling algorithm within physical machines are responsible to execute these applications. So we will look at each one of these separately, but the overall cloud resource provisioning, this one is actually responsible to communicate not only with cloud consumers, but also with these other components for a number of reasons. One is to increase the revenue to the owner. The other is to give good or very good experiences to the customer. So experience in terms of quality of service, cost savings, and so forth. So they have to work together. They're not separate. Okay? So what does the resource provisioning is responsible for? As I said, this part is called resource provisioning. So resource provisioning has a number of specific responsibilities. So one of it is this, to understand the user's needs. It is actually, there is something usually in between here called broker. Broker is nothing but basically an agent that talks on behalf of the user to the service provider. Okay, so we can actually consider the whole cloud consumers as brokers. You know, they broker to themselves. So what resource provisioning does is, from the service provider's perspective, it is the interface between the service provider and the broker or the client users or the cloud service users. So because it is actually acts both as admission control, because if these two report, there is a lot of issues and we are going to miss some of service level agreements. If they communicate with resource provisioning, it will not allow new jobs to come in. Even if it is on the process of negotiating with potential users, it will probably reject it. So it is actually acts in a number of capabilities and capacities. So I'm just listing here some of them. So the admission control that it does, I haven't talked about here. You can see only that it needs to understand the user's needs. Why? Because the users most of the time don't actually know what kind of virtual machine they need. There are different types and different sizes of virtual machines with different memory size, different CPU requirements, and so forth. So one of the reasons is it actually makes sure that the users get the required number of virtual machines. So it wants to match the workloads and quality service requirements of the user as with the existing environment. So it acts as a negotiator also on behalf of the service provider. It negotiates terms, service level agreements, with as well as payments with the cloud service consumers. So basically, what you can see is that here it simply communicates with the cloud service provider and communicates with other resource management components. So any decision that resource provisioning makes any mistakes, that then it's actually going to drill down to the rest of the systems. So if it makes a wrong agreement with cloud service providers in terms of quality of service, then these guys may not be able to meet that quality of service requirement. So that is one of the reasons that the alignment between these resource management components have to be very, very strong. Okay. So, what is resource allocation? Now, resource allocation, basically, the allocator is basically responsible to select an optimal set of physical machines to host the received services. So, user says, I want 5 virtual machines. Okay? Then resource provisioning will wake up and say, okay, I can provide you these 5 ones. Right? That's where it stops, beside other things that we talked. And now the whole thing is passed on to the resource allocator. Now, resource allocator will say now, okay, who should I send this? Mapping, it is a mapping problem. Who should I send this to? I have a number of physical machines here. Which one of these are actually going to run this application, this virtual machine? Taking into account the jobs that are already running, the quality of service requirements or service level agreement that already exists, and the owner's criteria for maximizing and minimization, such as power conservation, such as increased utilization of the resources. So it takes into account all this and then makes the appropriate mapping of the user virtual machines to physical machines. It also plays a major role in terms of resource virtual machine migrations for load balancing, for energy management, and so forth. So again, I'm just listing just few of them here, but there are a number of important tasks that it performs. Okay, so the last one is the physical machine scheduling. So virtual machines are mapped on the physical machines, where depending on the sharing of the resources. So every physical machine can be shared in 2 ways, along space or along time. So space means that one task or one virtual machine will run on one physical machine. Time sharing means multiple virtual machines will share one physical machine. So depending on that, and depending on the rule or policy that we designed, the virtual machine scheduling will execute that job, making sure that each virtual machine will get the appropriate service in the physical machine. So this is actually the differences between these 3 components. I have mixed it, I will continue mixing them, I will also today mix them. But these are the clear separation of what they do. Each one of them do this. Now, many times, we actually combine them. We combine them as resource provisioning, we combine them as task scheduling, we combine them as resource allocation. But in terms of proper discussion, we need to actually make sure that they are different. Okay? Any questions so far? No? Okay. Now, why actually we want to do resource allocation or resource provisioning or virtual machine scheduling? Now, the problem is when you explain it, or in plain English, is very simple. I have a set of jobs. Now we can get into different aspects of these jobs, but we have a set of jobs, and we have also a set of resources. We simply want to assign the physical resources or virtual resources to this set of jobs. Now, it becomes very, very simple. But there are certain constraints that we must satisfy. So, these jobs that I just told you, they may be one job, which is indivisible job. Or they may be divisible jobs that have many, many tasks. Okay? Now, one of the constraints, maybe, from the user's perspective, is the jobs, all these tasks have to run in parallel. They must run in parallel. At the same time, start at the same time, finish at the same time. This is the simplest you can see. But how does the system will achieve this is another issue. So there are a number of other constraints, many constraints. Yesterday I showed you about 3 or 4 when I formulate the problem. The day before yesterday I showed you 3 or 4. So you can see that they are the objectives that you want to, the problem itself and the objective you want to achieve, and under what constraints. These are the 3 important components of any scheduling algorithm. You have set of jobs, set of resources, and the objectives, which means, objectives means basically what you want to achieve. Do you want to minimize response time, cost, or do you want to maximize utilization or whatever? But the third component is the constraint. Under what condition I want to do this? This creates a serious problem, particularly with systems like cloud computing. Why? Because, for example, you can pack 2 or 3 virtual tasks on virtual machine. 1. You can also, the jobs can come in random fashion. Okay, these jobs, some of them big, some of them very small. Okay, then the system can fail. Some of the systems can fail. Power can go off. So these are some of the issues that you see. But under all these circumstances, you want to optimize. There is quality of service requirement, there is cost involved, and so forth. And the system is dynamic, right? Because people are purchasing it. They can purchase on demand. The way yesterday we covered the advanced resource scheduling algorithms. There is spot instances that we discussed yesterday. All this dynamic environment creates another level of problems. So, scheduling becomes an optimization problem. It is an optimization problem. So, the size of the resources creates another problem also. It's not 1 or 2 or 3 systems that you are actually now looking at. It is thousands. Okay? Now, Google Data Center claims to have in excess of 44,000 servers. This is just, we believe this is just the small number. How you actually going to allocate on this scale? All distributed systems scheduling were actually developed before us on systems of maximum 512 CPUs, which is called parallel or distributed computing. Then came the great computing of thousands. Now we are talking about hundreds of thousands of machines. So this makes scheduling from cloud perspective much more difficult. Okay? So it is a very challenging and very difficult problem. Before we could actually live when first search engine like Yahoo came, we could actually send a query and wait for 5 minutes, it was okay. Now, none of you can wait a second. You will turn off the search engine. Why? Because that level of expectation is there. So how can we actually, that expectation, that satisfaction automatically translates to cloud service users, right? These guys need to be satisfied with the service they're receiving. So how can we actually achieve that? Be it in terms of response time or appropriate costing, how can this be achieved? So all these issues that I just told you makes scheduling or resource allocation an extremely difficult optimization combinatorial problem. So these are some of the optimizations that we want to achieve, but optimally achieving these optimizations, it is extremely difficult, and it is NP hard, NP complete problem. Okay, so what we mean by NP hard and NP complete problem is there is no algorithm that can optimally solve this problem. So we can't solve it in an optimal manner. Why? The search space is extremely big. And if you remember, he asked me a question, how can we implement meta heuristic because of that search space? That creates a very serious problem. Okay, it takes a long time if you try to search the different combination and come with the optimal solution. Because there is no, now optimization algorithm can be roughly divided into two categories. So the exact algorithm and heuristic algorithm. So the exact algorithm can actually guarantee you the optimal result. So they are designed in such a way that they guarantee they will find the optimal solution in a finite amount of time. Okay? But for scheduling, this is already proven to be NP-hard optimization problem. This finite amount of time may increase exponentially in response to the dimension of the problem. So we can't solve it. That is why we actually use heuristics. So most of the algorithms that you see are actually heuristic algorithms. And heuristics algorithms don't give you this guarantee. They will not find you the optimal solution. They will find a solution very quickly, but it's not optimal. So when you see many different algorithms that I developed, that Professor DP worked on, Professor Zar worked on, they are heuristics but different, because heuristics are actually applicable to a specific problem and every heuristic can produce many different solutions very quickly. So my algorithm may be different than Professor DP's, but his is faster than me, because somehow his can find one of the solutions very fast. Okay, so the challenge is when you see the algorithms that are very similar or out there, they are heuristics. They could be similar, but there is a lot of issues behind the heuristic algorithm that you will see. So as I said, heuristic algorithms usually find solutions good one, and also in a reasonable time. You don't have to wait for it as long as the other ones, but sometimes they're not. Sometimes they are clearly suboptimal. You can see them. Now, we can actually prove algorithm is not polynomially solvable mathematically. You can't do this for this. Heuristics algorithms usually are adapted to the problem at hand, so they are specific to a particular problem. So you can't actually take one heuristic and then adapt it to, say, for example, the algorithms that we developed for grid computing with a specifically heterogeneous environment that we built into it, and then come and try to run it on cloud computing. That heterogeneity must be stripped off, because now we are looking at virtual machines. Even though the underlying system, the physical machine, can be heterogeneous, but the virtualization actually makes it much easier to work with the physical systems. So also, because we are bringing, we can't directly adapt heuristics, we need to actually modify it. And heuristics are always too greedy. Okay? They usually get trapped in a local optima. This one, I'm happy to discuss if you wanted. There is something called global and local optima. But at this stage, you really don't need to know. You really need to know that this algorithm is greedy. It will give you good solution in a respectable time. Okay? Now, this is where you will see most of the algorithms that are heuristic differentiate from one another. The assumptions, the underlying assumptions they make. Because in order to develop heuristic algorithm, you need to relax some of the constraints. Okay? So if, say for example, someone wants to run an application right now and get it back in 15 minutes, this may not be possible. So we can actually relax this. We can say this is not possible. Under our algorithm works under the assumption that the user does not require the response in 15 minutes. So basically, what did I do? I simplified the problem. I removed one of the constraints. So we make a lot of such assumptions to develop an algorithm. Again, but the issue here is how much simplifications you make. So if you're too generous, nobody will actually accept your paper. If you're too hard, you will never finish it. So it is actually a balance that you have to make. Remember, you are solving a problem at hand, and you are designing a heuristic algorithm to solve the problem that is in front of you. Don't make a lot of simplifying assumptions. Your heuristics has to be as close as real life situation, as much as possible. Okay? Now, when you develop resource allocation and scheduling algorithms, you need to get extra information. Usually, we simply get the problem, sit down, and rush into it, solve it, write, and send, try to publish it. No, there are more than that. That should go into the development of your heuristic algorithm. if you look at this, for example, this actually shows the patterns that, and this one shows the spike, the pattern that the workload comes into the system. Okay? So, if I say all the jobs come at time 0, it's not real, right? What is in front of me is different. Yes, a couple of them can come at the same time, but the majority of them come in a different manner. So, it is very easy to actually, by looking at this, it's very, very easy to simulate this, to model this. So if I get this, I can actually immediately see something very similar to normal distribution. I can say this, I can come up, I can model the workload as a normal distribution. And then I can justify why I actually modeled my workload as a normal distribution, because this is a real system log that shows it is normal distribution. So when you design algorithm, particularly heuristics, and particularly when you make assumption that I just made, you need to support your claim. One way that you can support your claim is by having extra information at hand. Okay? So, you can also see this one says the spikes, most of the time it is normal, but there are very high spikes in the arrival time, this is daily demand, and this is the varying workloads, different workloads. So you can see that by just looking at this, I can also say this is very, this is what I've been trying to pass on to you before. This can be simply modeled as a two-stage hyperexponential distribution, because I can see most of it are small with some very big ones. This again reflects a real world situation. So you need to collect information like this when you actually design anything, any heuristics. So you can actually, you yourself will actually feel comfortable to say my algorithm, my heuristic is as close as the real life environment. You can't simply design a resource allocation in a vacuum. Okay? Now, these are another set of challenges that cloud computing brings. Okay? We had this problem in terms of what they call now multi-tenant. We used to call it time sharing. So it's not new, but now it is done for money. Okay, and for also for energy, consolidation. But it is known before. Okay, it's just the name change. But in terms of resources, the scale is very huge. We have not worked with this level of huge resources before. Okay? Elasticity, dynamicity of the resources, and also the workload types, the variety of workload types. Requirements, user requirements are different than before. And every year it's getting worse and worse, because as soon as they get used to the system, they expect more and more from it. How about cloud users' job that often requires cooperation among multiple virtual machine instances? Most of the time we simply say, here I have virtual machine, it's running fine. But most of the time these virtual machines communicate with each other. They pass data to each other. If you look at workflow applications, they always pass data. They also sit and wait until the parent finishes the work and send the data. So, do you want, if a virtual machine is sitting on physical machine, do you want that machine to simply sit or do another work?
Do another work.
If you have to say it has to do another work, you have to also make sure that that particular job will be evicted as soon as the data comes. Right? So your algorithm now becomes a little bit
Harder.
sophisticated. So these are the kind of issues that you need to actually understand and take into account when you design and develop your scheduling algorithm. So as I showed you, the arrival of the jobs to cloud data center is not batch, is not smooth. It is actually, as you can see, stochastic. So you need to actually take into account that situation as well. And the workloads are not all bag of tasks, embarrassingly parallel jobs. No, you have small jobs, big jobs, jobs that only takes maybe seconds. So a variety of jobs. When you run your application, when you run your experiments, take into account all these. What happens if I actually run a number of applications on top of that? So you need to understand the workload characteristics. Okay. In particular, what do my application need in terms of virtual machines? Okay. So I have seen papers that actually simply says my task runs for 10 seconds and it needs it buys medium virtual machine from the Amazon. The paper modeled Amazon very well with the size of the virtual machines. But he's saying his task only takes about 10 seconds or 10 minutes, I can't remember. But and it is independent task. So when you look at the medium virtual machine, the memory size of the virtual machine, the CPU time it uses, you can see that there is mismatch. So you need to actually understand the your workload characteristics. Is it actually reading a file, or waiting for a file, or writing a file? Okay. What are the capabilities of virtual machines that is mapped to your applications? So this is what I just told you. If the capabilities are underutilized, you are in problem. If overutilized, is also a problem. So you need to actually make sure that it's good. They are now also, you need to come up with appropriate objectives. So we know that these objectives are divided into user-centric and service provider-centric. So say, for example, the service provider wants to optimize energy and revenue. And on your side, you want to optimize cost or response time. I think I've already talked about this. You can see that these virtual machine types are also very important when you do your experiment, not only in terms of how much they cost, also the size they consume. Okay, so it's better to, instead of getting, say, large one, it's better to get a small one. Any questions?
Sir, I have one actually small question. Usually, when we design scheduling policies, in literature we see, for example, in grid scheduling, many times I have seen that they say that the scheduling problem is NP hard.
Yes.
As far as cloud is concerned, sometimes they say NP complete, sometimes NP hard. Well, it's again a fact that if it is NP hard, it's bound to be NP complete too. So what's your take in it? So if we have to, tell somebody, or discuss with somebody, is it NP complete or NP hard?
You already answered your question. You said if it is NP hard, it's bound to be NP complete. But it is actually the way you frame. If I actually frame my problem statement and the objectives and the constraint, I can prove that it's NP complete. And also, if I if I want to make it NP hard, I can also now formulate the problem to show that it is NP hard. So it is actually, the decision is what you, the way you formulate the problem. But the best answer, if somebody asks me, is I would say it is a combinatorial optimization problem and very hard to solve. Whether it is hard or NP hard, NP complete, they all become one at the end of the day. It's just the semantics that people, particularly optimization people, want to use. For me, it's a very difficult problem to solve. I have used both formulation to show it is NP hard, and sometimes I use to show it's NP complete. So it is. So I don't know why I do that, but from today I'll be mindful. I always just follow whatever I have in there and see, and try to prove it is NP hard or NP complete. That's a good question actually. Any other questions?
So when it becomes NP hard and when it becomes NP complete, you formulate.
Yeah, you formulate your question and the objective. You can actually show it is NP hard.
What are the conditions which makes it NP hard and NP complete?
There is no specific conditions. It is a combined. The combinatorial problems, most of them say when I wanted to say it's NP hard, or say for example I wanted to show it's NP complete. So what I will do is I will actually formulate my problem in a very similar problem like bean packing. And bean packing is, we know, NP complete problem. So I will just say my problem can transfer into this problem and show that. That makes it NP complete. So if I wanted to show it's NP hard, I'll take very similar approach. I show that, say for example, one problem is NP complete, and I'll show my problem is also easily transferred into this problem and show NP hard. So this is what we do. There is no specific thing that says if you have this, this is NP. If you have that, this is NP hard, NP complete. It is always the transformation of the problem at hand into already known problems to be NP hard or NP complete. No, I didn't answer, right?
No, you didn't get the answer.
Okay. Any other question?
I have some request rather than
Okay.
question. Like this, the whole resource management,
as has been divided into resource provisioning, resource allocation, and then VM placement, VM mapping.
Yes. Yeah.
So then research issues are also different
Yeah.
at the different places. So better if, I mean, the whole audience can understand what are the research issues among all these things.
I have been doing that. They got yesterday. How many you got? Research problems, open problems. I do that at the end.
Okay.
No, I don't do it in the middle.
Achha. Now another thing is that well, let's say placing VM on physical machines. Now physical machines now as of today are having many type of configuration. Then the problem also changes. Like if you have multi-core machines, how many cores are there? Then whether you have the time sharing of the cores also or not. And the problem also, the kind of a workflow that you have, whether it can be parallelized or what are the dependencies, etc., etc. So I think if they can better understand once these are, let's say, detailed in fine way.
But to do that, they have to understand the mechanism. If they don't understand, if I don't explain the mechanism, and if I straight go into there, then the first 2 days I did that and I got good feedback and I came back and redid the whole thing. So I'm just following that. I can go into high end the way the professor is saying. Which one you want?
Maybe start the next week we can delve into more specific areas like let's say for experiment for 1 day.
Yeah.
Till then we can decide.
Okay.
Because there are many other things also to be discussed, like the meta-heuristic
Yeah.
part, then energy constraint resource provisioning.
But those ones are coming. What he just requested is they coming. They build on these ones. These are the you see heuristics. Every one of you will design heuristic. I know this for sure. But the problem is you need this information to design them. If you don't have this information, you just do it. So and so did this way. I'm going to tweak this algorithm and just run it. But to show that algorithm, the original thing, the first thing what you need to do is the algorithm you just see is lacking something. So to add something, to extend that algorithm, you have to have this whole background. If you don't have that background, you actually will not be able to even extend it. So I could actually list a lot of heuristics algorithm and the issues with heuristics algorithms, the open problems about heuristic algorithm. But heuristics algorithm is heuristics. You have your own problem, you actually design to solve that problem. But to solve that problem, you need this background and this information that I'm giving you. It is when it comes to like dynamic resource provisioning. What are the issues? What are the open problems? How do you do them? How did the others do? What should I need to take into account? But heuristics tend to be usually heuristics. Every heuristic is the same. The same in what I mean is that everyone can design heuristics. Okay? Now, if you see things like this, this virtual machine type of, many people don't actually consider this oblivious to virtual machine type. I can actually pull many papers that to just show you that they don't actually talk about which type of virtual machine they're using and why they're using it for. Okay, so you can see that there are different types and also different sizes, clusters. Each one of these makes different impact on the scheduling algorithm, the resource allocation algorithm. So you need to consider this when you actually come up with heuristic algorithm. Now we classify resource provisioning into static, dynamic, and hybrid. Okay, so one of the most widely used static resource provisioning is basically they consider the system, say for example, the arrival of the jobs are static. The usage of the system is static. No dynamism in it. It doesn't change. The virtual machine doesn't share the CPU with any other virtual machine. So everything is static. As I will show you, this is not actually true in cloud environment. Dynamic resource provisioning is another level, another type of scheduling that we use. Now, to design, the static algorithm are easier to design. But dynamic algorithm is very difficult to design. Okay? Design, testing takes long time because as soon as you change something, the whole thing changes. And you need to keep that into account. Hybrid is actually combining them. Okay? So when to use static and when to use dynamic algorithm. So the provisioning, the planning type is also very important when you actually design algorithms which for cloud specific environment. Now, static resource provisioning has problems. Easy to design, but these are some of the problems you will see in static resource allocation. Now, because you scheduling, if you have 10 tasks, you can actually say, I just need 10 virtual machines. And these 10 virtual machines, your job is basically is not growing. But if it's changing, you can't. So you get into what is called under provisioning. Right? If you say, okay, my job as it's running, it will increase, then you can't change it. So you have to buy more resources initially. So that is over provisioning. Now, if you see the problem, one of the problem of over provisioning is, or under provisioning is that the users will not be happy, right? Because if you under provision, there is probability of missing service level agreement or quality. But that is not actually very nice from client's perspective. So the service provider has to design the appropriate scheduling algorithm to ensure that the under provisioning will not occur. So when you design a static algorithm, make sure that you don't get into these situations over provisioning and also under provisioning. Okay, so static algorithm is very easy but very poor in terms of if the system is dynamic. So most of the static scheduling algorithms are used in private clouds or big data centers with what do you call parallel machines, supercomputers. That's where you actually use them. These are some of the rule-based heuristics. Many of you have seen these ones, right? So there is first come, first serve, minimum completion time, minimum execution time, maximum min, minimum min, and average. So where do we actually use these ones? Anyone? Yeah. Do we use them at the resource provisioning, resource allocation, or virtual machine scheduling?
Scheduling.
Mostly for the batch of jobs.
It is mostly on the batch of jobs and at the virtual machine scheduling. That's where you see them. Okay. Now, these ones are internal, right? Internal to the physical machine. That's where they run. So they're not on top of the the physical machines, which basically allocates virtual machines to physical machines. If we compare, which one is, how do we compare? How do we compare scheduling algorithms?
Make a span.
Huh?
Make a span.
That's all objectives.
Yeah, it's objectives, right? So the objectives where we compare. Now, sometimes we talk about fairness for the jobs, right? So first come, first serve is the most fair, right? Because you come in, you get this. So these are the kind of things that you need to consider when you design. What is the objectives for scheduling? How do I compare my algorithm with existing heuristics algorithm for task scheduling? So this is the question I got yesterday, at least from 3 people. How can I compare my scheduling algorithm? Now, because your scheduling algorithm is heuristics, and as I told you, that because you are solving a specific problem, you need to actually make sure that that scheduling algorithm will run in the same environment you have, on the same application, okay? And does the same thing. Because it is very difficult to compare orange and apple. If you take one heuristics and then you try to compare with your own heuristics, then it is not actually good. You need to make sure that they actually run on the same application in the same environment. Okay. Now, interference aware task scheduling. Another, the multi-tenant that I talked. Now, multi-tenant from cloud perspectives is now, is as I said, is time sharing. But now, time sharing between virtual machines. And virtual machines can actually have 1 or 2 tasks. So this is actually the difference in terms of time sharing that we have used before. So if you pack 2 tasks on a virtual machine, okay, so now becomes this virtual machine will run on the CPU and get evicted. So in that case, either not both of them run, right? It's only one of the task runs, and then the whole virtual machine gets evicted, and this comes and run, and the whole virtual machine gets evicted. And then if task 1 run, now task 3 runs, and then repeats this. Okay? Now, a research question. how much tasks can we pack in a given virtual machine. This is an open problem. How much? Without actually, now you need to make sure that without radically affecting the quality of service or service level agreement.
It depends on the nature of task.
Huh?
It depends on the nature of task which we are going to do.
Yeah, usually what we do is, remember, a virtual machine is assigned to one person. You can't actually bring in another person's task and pack it in there. It's just your task. Sharing can happen between two different virtual machines, between two different people's virtual machines. But the issue here now, that is already a solved problem, it's time sharing. The open problem is actually sharing one virtual machine between the same owner's tasks. The research question is how many we can pack, taking into account that this virtual machine has finite resources, right? Memory is restricted. The owner wants to optimize, that's one way of optimizing utilization, but there is possibility of impacting service level agreement. So now, how can we actually determine the optimal number of tasks to pack on one virtual machine? So by packing, what do you achieve? You achieve lower cost to the owner because you buy one virtual machine. But at the same time, if they take long time to run, because depending on the plan you use, if it is pay on demand plan, you pay per hour, right? If you actually use that, and if it takes you longer time, you will end up paying more. So the question to you is then, how can we optimally solve this problem? Is the question clear?
Yes, but this it's not belong to cloud provider. It belongs to customer.
No.
How he can manage his task, because he will take VM. But it depends on him how he will manage his tasks inside this VM.
Yeah, but if the cloud providers, if you see the business model nowadays, if you make the client happy, you will get more clients. So it doesn't matter whether the client does it, but the most important is a research question. If you see nowadays, they even pay you if you bring somebody as a customer. They will say, bring someone, we'll pay you. So the better the system is, the more customers the cloud service provider will get, and also the lower the price is, because the number increases, is economy of scale, right? So the price decreases and then more customers. If you say this is your job, you must do it, then 99% of the cloud users don't know how to use it, how to do it. It's just like mobile phone. Most of us don't know its capabilities. We just use it for phone or watching movies, but there are other many good and bad capabilities. So even though user, like he said, it's user's issue, I believe it is more on the system service, cloud service systems issue. Because the user can say, I want to run my application on cloud services. So it is the cloud services' responsibility to ensure that this application runs as cheap as possible and without violating the service level agreement or quality of service. But this is an open issue. What I just told you is an open issue. how can we actually address this? Maximally, optimally packing them. So remember, there is both objectives, both sides of objectives get affected. User thinks he can save money by using fewer virtual machines, but if it takes running longer, the user ends up paying more. So we need to take into account that part of the problem. And on the other side of this problem, we need to also make sure that we can't assume the CPU and the memory is infinite. It is finite. There is a problem. Is that question? Any question regarding this problem? Okay. Now, the second question is, what kind of application we can pack? Not all applications are suitable. We know bag of tasks they can pack because they're the simplest one. But there are other applications which are actually very suitable for this. So I can see that workflows are somewhat okay, but there are applications called pipelining applications. So we need to actually find also what kind of application is suitable for this in addition to bag of tasks. Okay? Any question?
What are the characteristics of such a GIAN in order to accept a kind of application? So what kind of application generally it may hold or it may pack in?
That's what research question I told you just now.
No. What are the constraints? I mean,
Constraint is good. Constraint because each virtual machine has certain memory, right? So if you look at this, you see here, this is restricted and this is restricted. So you need to take into account this when you pack the number of tasks in there, always. This is one of the constraints you have to specify in formulating the problem. Okay, otherwise you get into memory thrashing. Now, the other thing that we need to actually look into this, which these people didn't solve, is the level of interference. We know that they have shown that there is interference when you run multiple virtual machines. There is interference, but what is that level of interference? Particularly if we use different rules. Say now what they did is basically they say every virtual machine shares the resource equally. Okay, so you run for few seconds, you give the virtual the resource back to another one, and you do this, but what is the level, particularly if this equal sharing is not applicable? So an important question here is, if we pack 3 tasks on one virtual machine, This becomes what? Big, right? Big job. And then you pack two machines, two tasks on virtual machine, much smaller, right? So from what I showed you that the smaller, this bigger task will take long time to finish. A research question for you is, can we actually see, let's say this is the one we packed two, the one that's packed two, can run with, say, minimal impact on this one, on the large one. So if this virtual machine 2 finishes, this virtual machine can have the whole machine for itself, rather than sharing with it. So in other words, what I mean is that the large jobs, let's take a queue, right? A queue. So if there is a big job and a small job behind it, then this small job may take long time if you just run the long job, right? If you switch them around, this small job may have very little impact on the long job, whereas the big job can have very serious impact on a small job. Can we actually do something in this virtual machine environment?
Can you apply the concept?
No?
Prioritize the task. Sir, can you apply the concept of round robin scheduling here?
Round robin scheduling is what I just told you. Everybody takes turn, right? You go for 1 minute, I'll go for 1 minute, you go for 1 minute, I'll go for 1 minute. But what we're saying is that one is very big. The small one can actually say, if you give it to me, I will finish it within 3 seconds, and then you can have the whole CPU for yourself.
Prioritizing the task. Shortage of first scheduling can be applied here?
No, you're talking, these are the old ones. This is new questions. The shortest job, we are not now in the queue. We are actually virtual machine on the machine level. On the queue, resource allocator allocates. Now we're talking about virtual machine scheduler. On the queue level, we have already finished that one. We actually now have these two big jobs, one big and one small job, sharing the physical machine. We want to actually see how optimally these two tasks either share the system or one compromises to make sure that they will, at the end of the period, they both will actually make gains, substantial gains. If the big one runs with the small one, the big one also gets affected, right? But if it has the CPU for itself, then it will be good. So the condition is when and under what condition we can actually allow the big job to simply say, I now will give you to run the CPU alone, and then I will take the CPU for myself. Now we come into the problem called bin packing, which is NP complete, which is actually an open research problem. But we want to do it in a dynamic environment because the CPU is changing. Is that clear? So these are what kind of these things these people didn't do. So we know that there is interference. It has been proven, but we want to actually solve it. Another thing they did is they worked on the prediction, the interference prediction, which is a very nice problem. Okay? Now, they used different models, linear model, quadratic model, exponential model. Again, this is done offline. So what they basically want to do is that two tasks, two virtual machines can run on the same machine, but they want to predict how much impact, how much interferences one will have on the other. But they did this in offline fashion. Okay? So they used historical data and traces and to actually predict that if this task is very similar to, if the sharing tasks are very similar to what historical data is, then this kind of interference will occur, so avoid it. So the whole idea is that you have the resource allocator that sits on top between the resource provisioning and the scheduling will sit there, will use this. Before it actually allocates a virtual machine, it will use that information, the predicted information, to either assign this job with this virtual machine with another virtual machine on this particular machine, physical machine, because there is no impact on it. But if there is impact, it will say don't assign them differently. Okay? So this is done offline. Is it possible to do it online? I believe it's possible. So remember I told you, you need to understand the characteristics of your workload to design algorithm. There is information, some information that you can actually use, and then some information that most of processors, CPUs, when they run, they actually collect information. They always monitoring information is in the log. Okay? The allocator, the resource allocator, can actually use this information with probably additional information and make online estimate or guesstimate and predict. It is doable. Can we do it? So all you need is actually the workload information. And then the CPUs, what they're doing. And information probably, workload that is running currently on the system. So there are many information that you need to collect. So the challenge is how much information you need. But because we're doing it online, we want to do it very quickly, right? So even if we get 80%, 70%, 60% right, it's good than what's currently available. So how much information, what information you need, how much information you need, how fast you can do it. Okay? Any question?
So in this case of prediction, we can use the machine learning algorithm.
Offline.
So what's the issue with doing it online? I mean, if I can reduce the time to predict, then I can deploy.
Machine learning is usually, we do it offline, so they did it offline. The issue is because when you finish, first of all, you need to teach. If you're using supervised learning, you need to teach it. You need a lot of data. But from what I showed you, the application may not be actually the same that the supervisor, the machine learn. It could be different. And then it won't give you the right answer. The second thing is that by the time your machine learning give you the feedback, the application is gone. It's already done. But online will tell you the application is already in the negotiation. We say, for example, resource provisioning step. You already know the information about the applications. Most probably you already know a lot of information is available for you about the physical machines and used virtual machines. Can we exploit this one just to do it right there before you allocate the tasks or the virtual machines to the physical machines? Offline takes long time, but we wanted to do it online.
That can be done by using master fascinator.
Any other questions? Okay.
So when we talk about this interference prediction model, so we use some type of the priority system,
Yeah.
like in order to avoid these interferences. So a type of the priority queue is created, like here we enter that particular task in that priority queue. But nowadays this memory gets cheaper, so this another problem comes that we have the long queue. So here this another type of the problem comes that the time that is spent inside the queue. Suppose that we apply some type of the priority criteria and we put that particular task into that particular priority queue. Now since queues have the bigger memory sizes, so they are type of the another type of the priority algorithms that we should apply into that particular queue. The time that is spent in that particular queue that also affect the performance, I think.
The waiting time.
Yes, so the waiting time in the queue.
Yeah.
The queue may be the priority queue.
Yeah.
But the time that is spent in the queue, so there should be this another level of this, you can the sorting required.
You can use that information.
Yes.
Yes, that you can. But this is a research problem that we need to exploit because it's not exploited right now. Many existing algorithms are actually offline or machine learning. Like he said, there's a lot of machine learning algorithms that do this. Not because it's not solvable, but because there is no niche. This is a very good publishable work. But many people just do the scheduling aspect of it, not the prediction. A lot of solutions now, if you look at failure prediction is going on now because if you have 40,000 machines, you can't manually find out which one failed, which one is working. You have to automate. The same thing, we can use that idea of tracing the failure. We can also use to predict it. That's what I'm saying. One of it is that to use the priority and waiting time of the tasks in there. So it is possible. But what are the question, the challenge is what are the appropriate information? And how much of it? Because some of it is a lot. If you look at the log, it's too much. But which one of this information and how much is important? And then how can we formulate, we developed it in such a way that it's quick online. Is that clear? Okay.
Moreover, the concept of the priority, etc. See, the cloud, you are supposed to have the big, whenever you require, you can scale it up.
Yeah.
Right, so why to wait for something?
Yeah.
Right, so the priority, the question of priority, etc. It's not that very severe in cloud computing as I think. Right, because you can scale it up anytime and scale it down depending upon your requirement.
Yeah. Yeah. But it's good to explore. You see, what Professor says is that these are not necessary. This is another idea that you need to take into account, right? Remember what I said, there are things that you need to develop, which I listed some of them. There are some that you don't need, okay? Okay, so we have talked about this. Now, remember I told you about the static scheduling problems, these two, that they have over-provisioning and under-provisioning. And if you have over-provisioning, you waste resources. We looked at this yesterday, practically how it happens. And here I said to you earlier, static algorithm leads to some satisfaction of your end user's problem. So we actually need to develop dynamic algorithm. There are not very many dynamic algorithms that actually consider the cloud and the applications, both sharing and incoming applications. So as you can see, the capacity with dynamic provisioning aligns with the actual demand. So can we actually design dynamic algorithms instead of static algorithms? Yes, we can. The issue is to understand the environment. So if you understand the cloud is dynamic, the workload that comes to the cloud is dynamic, the resources, the availability of resources is dynamic. But you can scale up because this is virtual machine, virtual environment. You can scale up as many as you want, even though we know that there is a limit in terms of virtual machines that you have in the cloud data center. But that perception is there. So because my environment is dynamic, then the most appropriate algorithm is a dynamic resource scheduling algorithm. Here is the issues, the most important issues with dynamic algorithm. Can you see it? No?
Yes, sir.
Yes? Okay. So the first question is when to allocate resources. Because remember what this will do. You allocate beforehand, right? You say, I anticipate 5 virtual machines. Why don't I allocate now, even though my application starts with 1? So now the other 4 will be unused. You pay for it. So this dynamics algorithm, to work, you need to solve this first question. When to allocate resources? And the second question is, how much to allocate? The third question is, which machines to allocate? Which resources to allocate? Okay? Now, give you the research question. Can we actually mix dynamic and static algorithm in a fashion or with the objectives of avoiding this? The static algorithm has some nice features, undeniable. One of it is simplicity. So, is it possible to mix, to come up with a hybrid algorithm that actually does both dynamic and static algorithm? This is possible in cloud environment because the resource management of cloud is hierarchical. So there are some areas that you just need to do it statically, and some areas that you must do it dynamically. Which are these areas that are open to static and that are necessary for dynamic environment? Okay? So, in other words, the hybrid algorithm, which I have done many, is basically uses time sharing and space sharing. So it combines time sharing and space sharing. Now take that idea and apply it to cloud environment, which we used it for grid environment. Can we achieve that? Okay? So, again, it is a very nice question. Now, there are a number of challenges which you actually face, particularly when you look at the application. Okay, dynamic environment, the applications are not the same. Not all of them are bag of tasks. They are completely different. A variety of applications come. And we need to take into account that different applications can actually work differently. And not only heterogeneous, but arrives dynamically. The workloads are dynamic in many issues. Interference is there. You need to solve this in terms of dynamic resource allocation, scalability, interplay with related application components. Now, you want to do this, you must actually satisfy these objectives, guarantee service level agreement and quality of service for each application, and for the cloud user, for cloud owner, you want to increase the utilization of the resources and maximizing system throughput. Okay. Now, if you actually design a dynamic scheduling algorithm, the algorithms that are proposed so far use on-demand scheduling planning. So in other words, they say, every time I want to run my application, the resource is there. All I have to do is I pay for it. Which is true, right? We looked at one way of reducing that payment is by packing the tasks in one virtual machine. But the other solution is to look at what is called spot instances. How can we actually integrate that in this? Now, you need to make sure that migration is implemented properly. And cloud computing does that beautifully for you. Virtual machines can migrate from one machine to another. Spot instances actually give you, say for example, for 2 hours, and then you get interrupted. When you get interrupted, you make sure that all your application is checkpointed and can migrate to another application if need be. But the open problem is, even all scheduling so far, you see, is on demand basis. Available, resource is always available for me. And I want to minimize the cost on that basis. But now we have different model, different structure of pricing. Can we exploit that? And to do that, one of another research problem I'll throw at you is, can we predict the lifetime of these spot instances? If we can predict that these spot instances lasts for an hour and my application goes for 5 hours, I better not to use it. Or if my application doesn't matter, it's batch oriented, can wait for another spot instances, then I can use for 1 hour, make sure that I then try to get another spot instance and move it there and continue doing this. So can you do that? Again, this is an open problem, a nice problem, and research now in spot instances is simply on auction. Okay, because spot instances is based on bidding. And a lot of work is just auctioning how to bid. but not actually to integrate with resource management. So I can see that for a long time nobody will do this integration, and you have a very good opportunity to work on a nice problem and get a nice publication out of it. How about, okay, using advanced reservation, again with dynamic scheduling. For advanced reservation, you pay for it, right? So in advance. The problem is you get into this issue, into these two issues. So how can you actually avoid this with advanced scheduling? By integrating it into resource management. Okay?
So why you are not listing the pricing as the objective, one of the objectives?
Because I wanted to talk SLA and pricing next week.
Okay.
I actually talked the day before yesterday, listed all the criterias, performance criterias. Okay, so we don't need this. Now, we talked about modeling, right? So modeling is also very, very important, but it's a hard problem, right? Whenever we design a new algorithm, we try to model first what we're actually developing. So you use a dummy data, a dummy data set, 5, 6, 7 data set, and then model with that, and then go into real one. Because if you start going in real one, it is actually very, very difficult, because the real data tends to be very big. It's difficult to debug your design and development. And in particular, you need to also model different types of the CPUs, memory, and how virtual machines, your application, how it impacts the virtual machine as well. Okay. Now, really, I have been talking about this reinforcement in a different manner so far. But basically, what this reinforcement says is that all the scheduling algorithms we have now doesn't actually have feedback. It just schedules and then looks for another one. It schedules and looks for another work and comes back. So, can we actually use this? There is Q-learning, reinforcement learning algorithms that exist there. In addition to prediction, learning from the mistakes it made, the good things it did, is very, very important. So, it basically, like machine learning, you said, can we do this? We do this in many control theories. It's not something new, but we need to implement it and use it in scheduling. Not many people does this. We talk about self-scheduling in cloud computing, which means, so he said earlier, the user is doing this and this. But now we need to loop, right? The control, the feedback. Maybe the CPU can tell the allocator, this is what is not good, this is what is it. Or the allocator can learn himself by using some information. Can we do that? And can we find out how much improvement we get? Can we do that with a static scheduler? Can we do that with dynamic scheduler? Which one is the best if we compare? What are the applications that can benefit most from this? This is one type of optimizations we have to do. Okay? So the other one is called, this is what I just told you in nutshell. This is Q learning. Okay? Estimate the future by using basically something like this. Okay? It's just a learning. I started with bad, but I don't repeat it. I must move always. So if I made something bad now, decision, next time I will learn from what I did now. It will be improved a little bit, and it will be improved a little bit. Keep going that way. Then, at the end, all your results will be good, because you have learned from it. So it's a technique, Q-learning is a technique that you can use to basically estimate quickly the future. Okay? Any questions? Well, this is the last slide I have. Now, what they actually did, this, is it a question?
No, I was wondering if I can go through these two papers which were like,
yeah, I'll give you all of them. Now, what basically they did is the reward system, reward and punishment. Okay, so they wanted, say, for example, an agent that is scheduling. So if you look at the from the remember I said the gateway that sits between the cloud users and the cloud system, the third party, I forgot its name. Broker. So it's just escaped my mind. So broker is an agent, right? Now what broker will actually does is the welfare of the owner or the welfare of the user, right? Because that. Now, if we actually can reward and punish these brokers the same way as resource management, if they do something good, we reward them. I mean, if they actually meet the objectives, we reward them. So the more you reward them, the more the objectives will be met. So can we implement that reward and punishment? They did very simple reward at the scheduling at the bottom level, but nothing above that. In fact, what do you reward the CPU? The reward should be actually at the level where the broker, which is on the user's behalf, negotiates with resource provision algorithm, the two make an agreement that actually meet the demand, the objectives of both user and the owner. Can we develop some sort of reward and punishment system there, so that we can actually optimize the applications that comes to us and the quality of service that the owner sends it to the user. So is there good thing if we implement these things instead of now simply saying the most they do is that I need this job to be finished at 9 o'clock, which is quality of service, and then the owner, the resource provisioner will say, so is it possible? It's very important. It's very nice problem also. Reward and punishment is done many places. Okay, but we haven't used that much within the resource management aspect. Okay, the only thing that you can see now is in negotiation. Now this also fits in with the sport instances I told you there very nicely, the reward and punishment. So can you implement that at that level as well? Can we do it? Yes, we can do it. The only thing is that the information I showed you earlier, what are the information we need? What is necessary to implement this? And how can we measure its impact and or its value? Okay? So any question for me? This is the light slide I have.
We have developed quite a few models in which we impose penalty on the service provider if they are not able to meet the services. And that penalty has been rewarded to the customer in terms of money only. Let's say. So that kind of a reward, or let's say the penalty at the part of the service provider, which is converted to reward to the broker or even to the service, the customer also. In terms of that. We have also done very similar work in terms of if you don't meet the service level agreement, the customer will be rewarded, you will be punished because we may not be get paid or some punishment is there. But this is actually if you miss service level agreement, right? But what we want to do is to avoid even getting into that. The reward should come on top, right? Because now what we're saying is that you promised, but you failed. Can we lift that up a little bit? My question to you is, from where it is now, can we lift it up and avoid this from occurring? Okay? I'm open. This is my last slide. I'm open to questions. It is quite possible to implement this kind of work. So even for good work, you are being rewarded.
That's what I'm trying to say. It is actually intuitive to think about it and implement it. So I even encourage you, rather than thinking some big problems that you have no background or you takes you long time, look at these intuitive problems that you day in, day out, you know it, you've seen it, you understand it. Can you actually take it and implement it? Has value, very important. You can get good publications out of it. In fact, if you see, most of my publications are very similar. The one I just told you, that's how I find problems and then just solve them. Very simple, very thing that I know, very much that I know about it. I know that about couple of you are actually writing proposal in this area. And do you have any questions, or did I clarify things? Hmm? Do you have any questions? No? At the back? Okay, so in the afternoon what we want to do is we take the cloud sim and implement first come first serve scheduling on it, and tomorrow, Monday when we come back, we will actually do dynamic scheduling on it. Okay, particularly the time sharing algorithm on it. So you can actually from that, once you implement that scheduling algorithm there, you can actually now understand to extend that to any of your scheduling algorithm that you want to develop. Okay.
जल्दी से कंफर्म कर दो तो नोटिस करना भी होगा सबसे बात छोटा है ना कल मैच कौन जीता था इंडियन फोन क्लाउड सिम 0.3.0 में एग्जाम्पल साथ में ही आते हैं, अब एग्जाम्पल 4.0 में अलग आ रहा है। नहीं सेम चीज़ है, एग्जाम्पल क्लाउड सिम 4 में बस यही डिफरेंस है ना, उसमें एक नया चीज़ ऐड किया हुआ कंटेनर, बस वही है। बट मैंने जो डाउनलोड किया है उसमें आई एग्जाम्पल अलग डाउनलोड करना, तुमने भी किया था देखो ये 4 है ना,
मैंने तो बड़े बड़े धक्के खाए हैं, आराम से भी मैंने किया मैंने।
देखो इसमें होगा भाई, इसमें देखे नहीं है। हाँ वो अलग से करना पड़ेगा, तो वही तो मैं कह रहा हूँ।
यहाँ पे रख लो ना, यहाँ पे।
तो उसके लिए क्या करें, दोनों को अनसिप एक ही फोल्डर के अंदर कर लें? तो मेरे लिए पूरा यही कॉपी कर लीजिए ना, प्रोजेक्ट डायरेक्ट उसको कॉपी पेस्ट कर दीजिए। ये प्रोजेक्ट तो प्रोजेक्ट को अच्छा पूरा ही प्रोजेक्ट डाल दिया तो पूरा फोल्डर देंगे ना आप, जहाँ पर आपने वो फोल्डर सेव कर रखा है। पेन ड्राइव कहाँ है? मेरे को
मैं क्या अंदर करूँ?
चाय वाय तो नहीं, ग्रीन टी
हेलो नहीं कहाँ पे नहीं, सारा सामान ला रखा है। दक्षिण में मैं बैठता हूँ लाइब्रेरी में, वहाँ पे एक बंदा आता है, पता क्या करने क्या आता है, हमने के लिए काउंट किया उसके साथ 41 सामान हुए।
41 41 आइटम्स
पीने के बाद लेगा तो बोतल ठंडी अलग गर्म अलग 10 भी अलग बिल्कुल सही है। कहाँ छप गया
इसको ऊपर इंडेक्स है जाना
ये तो सही लिख दो मतलब ये होगा पब्लिश भी होगा कैसे आप उसको दिखाएंगे ना कोई नदी को लगता है भाई हमारी तरफ से हाँ तो उनका 12 वाला भी देखने में यहाँ शादी कर रहा है
एक्सेप्ट भी होगा पब्लिश भी होगा
हाँ कहीं चलेगा
पूरा रेगुलेट हो गया अरे इसका कोई नोटिफिकेशन वैसे निकला है क्या?
मैंने बोला कि आपको वहाँ मैंने बोला तेरे आप कंप्यूटर साइंस डिपार्टमेंट से फिर वो कोई ज़रूरत नहीं है बस हम PhD स्टूडेंट हैं उनको बुला रहे तो आप अपने ग्रुप में डाल दीजिएगा।
तो नहीं कोई मेल है क्या? सर ने कोई मेल सर्कुलेट किया या ऐसे ही नोटिस कुछ है क्या?
ऐसे ही ग्रुप है हम लोगों का तो डालते हैं
कुछ डॉक्यूमेंट फाइल नहीं है या PDF फाइल उसको मैं मेल में डाल देता हूँ।
ये है मैंने बनाया हुआ
इसमें तो नहीं
अभी नहीं होगा ना
नया नहीं बहुत पुराना है
इंडेक्स की कंपनी अच्छी है और कुछ भी नहीं मैं इसमें प्रोडक्ट ले रहा हूँ एकदम
इंडेक्स हम पावर में यूज कर रहे हैं सही है एक्चुअली ऐसे लेते हैं इंडेक्स लोकल अपडेट हो गया ना या तो अपडेट पूरा नहीं हुआ या तो अपडेट चल नहीं रहा इन्होंने बंद कर दिया जावा अपडेट अवेलेबल है लेकिन होता नहीं
मेरे में भी 17 बार जावा अपडेट अवेलेबल जावा में टीवी